طيب بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله. السلام عليكم ورحمة الله وبركاته. First of all, I want to thank everyone for coming to this webinar today. I would like to thank the College of Computer Science and Information System in Najran University for arranging this event for students, researchers, and whoever might be interested in technology topics. I want also to congratulate Dr. Mohammed Alsulami for completing his PhD. Dr. Alsulami has received his master's degree in computer science from the University of Colorado, Denver, from the US in 2013. Dr. Alsulami has received his PhD degree in computer science and engineering from the University of Connecticut from the US in 2022. Dr. Alsulami's main research interests are in the Internet of Things, wireless sensor networks, clustering and pattern discovery, and also software optimization using engineering approaches. Today, inshallah, Dr. Alsulami will talk to us about his PhD work, which is titled Efficient Computing System for Underwater Wireless Sensor Networks. Thank you again, Dr. Mohammed Alsulami, for willing to share with us your work. The mic is yours. Whenever you are ready, you can start.
Thank you so much, Dr. Yusuf. First of all, I would like to thank all of you for attending my presentation. Today, I'm going to present my research work titled Efficient Computing Systems for Underwater Wireless Sensor Network. Here is the outline of my presentation. So, underwater wireless sensor networks have emerged as a new technology for underwater real-time applications. The underwater wireless sensor network is used to perform basically and monitoring of tasks over a specific region. It is equipped with smart sensors and vehicles that are adapted to communicate cooperatively through wireless connection. The underwater wireless sensor network is receiving significant attention and becoming a main focus of both researchers and practitioners. So with high technological advances in underwater wireless sensor networks, sensors have become smarter and smaller, and the ability to operate in various underwater applications. So here, 70% of the planet is water. So we have to have a technology that helps human beings monitoring and detecting underwater environment and any object of interest. So we have many applications for such technology. So I'm going to mention here some of them today. So the first application is for this technology is the environmental monitoring, such as pollution monitoring or monitoring of ocean currents and winds, improved weather forecasting, and detecting climate change. The second application is a disaster prevention and prediction. So we can use underwater wireless sensors to provide warnings coastal areas. The third one here, the third application for such technology is the ocean sampling, which basically in this application, networks of sensors can perform cooperative adaptive sampling of the coastal ocean environment. The last application here in this presentation is the assisted navigation. So this one here, sensor basically can be used to locate dangerous rocks or shoals in shallow water. So and mooring positions. So we have many requirements for this technology. So I'll cover today some of them. So there are some essential requirements. So the first one here is the longevity. Longevity, basically, it's about network lifetime, which basically is the key requirement for underwater wireless sensor network. So it has a significant impact on the cost, the time, and maintenance task, and performing underwater sensor nodes. It is crucial for maximizing the network lifetime, especially for mobile sensor nodes operations. Therefore, firmware has a vital responsibility in ensuring an effective practice of hardware features such as sleep modes, allows interruptions to replace polling, and easy to set up. In addition to that, here, Routing protocols and deployment of nodes have a huge role also in controlling the energy consumption. So it leads to a significant amount of research work on the development and evaluation process. The second requirement here is the accessibility, which basically so each sensor node communicates with each other within a communication range in the region. So the communication range is also another important requirement for underwater wireless sensor network, which affects the density of the nodes, the deployment feasibility, and the network cost of the targeted monitoring area. So after we finish talk about the application of this technology, right now I'm going to talk about the underwater wireless sensor networks traditional system, and then I will give an overview about the previous research work. So here, the underwater wireless sensor network comprise of nodes that are deployable on the surface and under the water. All nodes basically need to communicate and exchange information with each other in the same network and with the base station. Communication system in the sensor network involves transmission of data using acoustic or electromagnetic or optical waves media. So among all of these type of media, so acoustic communication is the most popular and widely used one due to basically to its attenuations feature in the water. So in regards of the challenge or the limitations of such technology, the first one is the limited bandwidth. So it's a main challenge in this technology. So factors such as multiple paths or path loss or Doppler spread can affect underwater wireless sensor network communication and lead to a limitation of channel bandwidth. The second point here as a challenge is the acoustic signal that basically does not propagate very well in underwater. So the propagation delay is a critical also challenge, particularly in the MAC protocol solution. So the last one, maybe here, the last one, or the third one here is the link reliability, which basically also another vital and important challenge for this technology, which basically if we solve this such challenge, we will basically increase or achieve high delivery rate in real-time scenarios. So the link reliability factor among the sensor node in the network can influence the delivery rate and consequently affect the transmission loss, which reduces the accumulated intensity of the waveform energy to propagate from the source to destination. The last one is the sensor heterogeneity. So it's a big challenge. So also this one enables cooperation of both mobile and static nodes in implementing specific applications, which also faces another challenge. So the challenge basically arises here in nodes communication halls to maximize the data transmission. In regard of the previous research work, I tried to cover some of them here. So some researchers recently developed some gateways deployment algorithms in underwater environment. So their network has sensor node that sense basically and monitor underwater environment. The big question of their research was where to exactly place candidate gateways. So they decided to fix the location of candidate gateways in order to simplify the complexity of the solution. So they fixed the number of the candidate gateways to a K number. They basically choose 25 candidate locations. So they studied the performance of the network in terms of end-to-end delay and the power consumption, so considering fixed number of candidate gateways. Another solution, they developed also another solution after that, another heuristic solution to determine basically the location of candidate gateways, because the previous solution is a little bit, it has very high complexity. So they decided to come up with something based on the knowledge of the field. So they use some heuristic technique. The first algorithm is, as I said before, it's a greedy. This one also also a greedy algorithm, but they searched among all candidate locations and find a candidate gateway that minimizes end-to-end delay and power consumption. But the second one, they choose the best two candidate locations. The algorithm then can exchange one of the already chosen gateways with one of the new gateway. As I said before, also, one of the limitations of the underwater wireless sensor network is the bandwidth capacity. So if a sensor node in the bottom of the ocean observes, for example, a huge phenomena, then the amount of the data to be transmitted from the bottom of the ocean all the way to the gateway will be very huge. Therefore, researchers developed some algorithm that can be used to place K number of processing nodes. So these processing nodes can process data locally and then submit only beneficial information. So the first algorithm they developed here is also called a greedy algorithm. So this algorithm, the greedy one, it's basically it starts basically by its objective is to find basically the maximum number of candidate processing node, which basically set to a number of k. I use a specified number here. So while the maximum number of processing node k has not been reached yet, then a sensor node is picked as a candidate node. The delay calculated to see if there is performance gain in terms of end-to-end delay. If there is improvement in the objective function, then this node is fixed as a processing node, and the available number of processing nodes get reduced by 1. This is for the greedy one. For the second one, they also developed another algorithm it's called a path-based algorithm. So this algorithm is almost the same, but actually they said there is some bottleneck in some of the routes. So we have to find the worst route, and then from there we can just basically apply some technique to eliminate or to minimize the end-to-end delay. So in this algorithm, their goal is basically to minimize the end-to-end delay. So the algorithm terminates when the number of available processing nodes reaches the maximum, or when there is no improvement in the objective function. This one, just talked about it. So the last one here is a layer-based algorithm. So in this algorithm basically is divided the area to layers. So the algorithm starts searching for the best node in every layer to be a processing node. Then it starts from the deepest layer and choose the best one. After that, it moves up to the upper layer and find the best node in this layer. So here is the algorithm. So before deploying a node in the upper layer, the algorithm goes back to the previous layer and checks the second candidate node. The combination that basically maximizes the objective function is chosen in this scenario. So, however, after they finish, they find the most two factors that negatively impact the performance of the system is the depth of the sensor node and the volume of the gathered data, because we have big data most of the time. So researchers named below developed some new algorithmic techniques in order to alleviate the impact of these two factors. So they developed another two algorithms, which basically based on the depth here and based on the volume. After that, researcher here at UConn, they developed also a real-time computing system as depicted on the right side here of the screen. So this system here, it's basically consists of sensor nodes, which basically gathered data in underwater environment. So master nodes here, master node basically collect aggregated data from the sensor node. We have they developed only a single processing machine for processing collected data and transmits valuable information to the gateway. This is for this one. So our research work started from here. So after they come up with this solution, we decide just to basically find another problem. So right now I will talk about my research problem. So as you can see here, as I said before here in the previous one, so the current architecture suffers from possible failure because there is only a single computer, and it is necessary to overcome such limitations. So adding computer is a significant step to handle the larger volume of aggregated data, and also to enhance the fault tolerance capability of our system. So after we define our research problem here, we will talk right now about, we'll move on to our next step, which basically research objectives. So as I said, there is not only a need to increase the reliability of the network, but also to wisely manage the deployment process of computers in the targeted area of the operation. So this could be done basically as by developing a reliable architecture, by developing also some fault detection and fault recovery algorithms. And we need to minimize the number of computers while we need to guarantee a higher reliability in our system. So also we need to increase the number of the computers to handle the additional load in the network as needed. So here, for the sake of the time here, I'll just try to cover the first slide because I think we still have around 60 slides or so. So here we have many slides for terminologies, but the first one is the most important one. So here we have sensor nodes, which basically that capture and sense data in our underwater environment. Cluster heads, which are capable of performing some gathering sensory raw data from their sensor nodes. And the computer node, which basically task is to collect and process data that passed from cluster head and then extract the valuable information. Sync node, the last one here, is the observing node, which basically collect all valuable information from the computers and process it locally, and then submit the remaining, which basically collect all the data collected from the computer in the system, and then submit it to the control station in the system. So after that, I'll skip these just for the sake of the time. If you are interested, just let me know. So here are our research approaches. So in this, after this slide right now, I'm going to introduce our reliable architecture, which basically we developed, and then I will start first by presenting the components of the architecture. Followed by I will also go over our fault detection and recovery algorithm. So here is our architecture. So in this architecture, basically sensor nodes are deployed in the targeted area. Then clustering techniques are applied for clustering the deployed sensor node into groups. So one leader to every group is assigned as a cluster head. So the duty of the cluster head basically here is basically to gather sense data from the sensor node that are in its group. Then the cluster head passes the collected raw data to a computer for processing stage. After that, every computer CI passes the passed data to a service gateway. Here is our the two metric of our system. So the first one is basically our metric to calculate the end-to-end delay in our system. The second one is the a metric for basically calculating or finding the power consumption in our system. So for the fault and detection here, as I said before, after we develop, right now we already finished and developed our architecture for the system, but we need to add some fault detection and recovery techniques to the system to increase its reliability. So how can we do that? We need just basically to detect a faulty node as following. So each cluster head collects data from its regular sensor node in the network. So after then each cluster head sends collected data to a computer CI that the cluster head belongs to, and waiting for the acknowledgement to come back from the computer. So if no acknowledgement received from the computer CI, another cluster head in the same communication range is get triggered to send a checking status message. So we keep repeating until all cluster heads in the communication range of CI are triggered. So after that, a voting process begins after all cluster heads in the communication range of a CI are triggered. So decision is made based on the majority. So if a computer CI is still functioning, a message gets broadcasted to all cluster heads in the range of a faulty CI to all CIs that in its range, saying this node or this computer is a faulty from now and on. This is for the recovery, for the fault detection technique. For the fault recovery technique, so we now start the process of recovering a fault in the system. So in order to keep the whole system functioning, so each computer has a communication channel. So when there are more than one communication range overlap, then we say that any node in this overlapping region is a common node between these crossing communication ranges. So a cluster head of a faulty computer may be considered as a point of connection to another computer in the network. So we choose a cluster head that falls in the maximum number of overlapping ranges. So in case there are more than one candidate cluster head, then one of its computers still has larger remaining amount of function is chosen. This is in regard of the faulty or the fault detection or fault recovery, sorry, technique. So in our simulation here, in this work, we deployed sensor node and cluster head in this area. So then we assigned every cluster head to a computer. The process of assigning every cluster head to a computer was by applying a clustering technique which I will talk about it in the upcoming slide. So communication ranges of computers, cluster head, and sensor node are set to 125 and 120 and 150 and 100 meters respectively. So we deployed here 100 sensor node. So here is the result of our experiment. We decide to use different number of computers to see the impact of our architecture on the network lifetime. So comparing to the last architecture with a single processing machine. So we observe that adding additional computers and applying a fault detection and recovery strategy would eventually increase the system reliability, because all of the work of the faulty computer transferred to another computer in the system. So the new architecture is more tolerant because the network keeps functioning even in the presence of faulty computers. Thus, the lifetime of the network here would be much better comparing to the baseline system. So main advantages of our system here, of our architecture: first, we discover and recover. We first discovering and recovering faulty computers. Second, with every additional computer, we increase the network reliability by 50%, as you can see in the right side of the slide here. So based on our proposed architectures, so today I present only a single architecture, the first one, but I have another two also architectures. But for the sake of the time, I only present one. So based on our proposed architectures, we need to at least deploy a single computer, but we may end up in need to deploy more than one computer. So how many computers do we need? And where exactly in terms of location do we need to deploy these computers? So in the upcoming slide, I will start talking about computer deployment strategies. But before that, let me just give an overview about some clustering techniques. So when we say clustering here, it's basically a method of unsupervised learning, which basically a common technique for statistical data analysis, which used in many fields. So clustering is often basically used as a data analysis technique for discovering interesting patterns in data. It is applied when there is no class to be predicted, but rather when the instances are to be deployed into the natural groups. So here we have our first type of clustering, which hierarchical clustering techniques here. So for this one, for this approach, we start first by computing the proximity matrix of data points. Then each data point is designated as a cluster by itself. After that, we keep merging the two closest clusters and update the proximity matrix. So this technique converges when a desired number of cluster is met, or when a single cluster remains in our data set. So for the second one, the divisive clustering technique here, it basically starts by including all objects in the beginning in a single large cluster. At each step of iteration, the most heterogeneous cluster is divided into two. The process is iterated until all objects in their becomes in their own clusters. So here we have some metrics. We have some methods or metrics that we use it to measure this distance between classes. So the first one is the single linkage method, which is based on grouping clusters in bottom-up fashion. At each step, combining two clusters that contain the closest pair of elements not yet belonging to the same cluster as each other. The second one here, the complete linkage method, is based on the maximum distance or the furthest neighbor approach. So at the beginning of the process, each element is in a cluster by itself. The cluster are then sequentially combined into larger cluster until all elements end up being in the same cluster. The third one is the average method here, which basically the distance method, basically the distance between here two clusters is based on the average of the distances between all pairs of objects. The last one is the centroid method, which basically the distance here is between two clusters is the distance between the two mean vectors of the clusters. So at each stage of the process, we combine the two clusters that have the smallest centroid distances. The second type of clustering here is the partitioning clustering. So in this one, which basically the second clustering here, it basically classifies the information into multiple groups based on the characteristics and similarity of the data. So the data analysis specify the number of clusters that must be generated for the clustering method. In the partitioning algorithm, when database that contains multiple objects, then the partitioning algorithm constructs the user-specified partitions of the data, in which each partition represents a cluster and a particular region. There are many algorithms that come under partitioning algorithms or partitioning type of clustering. So some of them are popular, such as K-means and K-Medoids algorithm here. So today I'm going just to cover one of them or two of them here. So the first one is the K-means algorithm. So this algorithm basically it works by first specify the number of cluster K, then we pick K random points as a cluster centers. After that, we start assigning data points to the closest cluster center. Then we find the centroid of every cluster and update the membership based on the distance metric. So we stop when no point assignment change. That's mean the convergence happens. So here we have an example. So here we have these data points labeled in green, as you can see it here. So we pick these 2 points as a random 2 Ks here. So then we start assigning data points to the closest cluster center. After that, we start calculating the centroid of every data point. So we keep repeating until the convergence happens. So this is for regards of the K-means algorithm. So the advantage of K-means algorithm is basically relatively simple to implement, and it scales to large data points. So, however, it's a little bit sensitive to the outlier. So, because of that, I decided just to talk about another algorithm, which is basically I made some modification on that algorithm. So, this algorithm is called K-Medoids algorithm. So, this one is basically when we say just only a K-Medoid, it's nothing but an object of a cluster, which basically holds average dissimilarities to all objects in the cluster is minimal. So centroid cannot be dragged by the outlier nodes when K-Medoids is used. So K-Medoids is more robust to noise than the K-means algorithm. So here is our modified K-Medoids algorithm. This is our contribution is here. So we developed here a modified K-Medoids algorithm to find basically the location of K number of computers based on end-to-end delay. So the algorithm starts by selecting K number of processing nodes, assigning each point to a medoid based on minimum end-to-end delay. We select a non-representative object in every T in every cluster. We compute then the total cost is of swapping the medoid M with the T. So if we find the delay is less than the previous delay, that means we have some improvement. So then we swap M with T to form the new set of K-Medoids. So we keep repeating until we reach the best delay or the maximum number of iterations. So here we deploy 66 master node with their regular nodes. So we fix the communication ranges for candidate computers and master nodes to 200 meter and 150 meter respectively. So the network area is 600 square. So as you can see in the right side here is the parameter of our simulation. So node deployment distribution or topology is fixed here. So we decide to deploy node in 3 different topologies in order to see the behavior of our algorithm on different scenarios. So we deploy nodes in the area randomly and cells-based and also semi-uniformly distribution. So our framework, our architecture plus our modified algorithm, which basically we call it our framework, can find the location of K candidate computers. One of the main steps in the framework is to use our proposed modified K algorithms. So nodes are deployed in 3 different scenarios, randomly in cells and semi-uniformly. And we studied the effectiveness of our proposed algorithm on these 3 scenarios. So the semi-uniform scenario is well balanced in terms of load between all computers or all different scenarios. Here is our second and third deployment strategies. So the second algorithm here is basically the first, we call it here, we have a typo here, algorithm 2, should be 2, not 1, but that's fine. So every master node has a communication range, which basically set to 150 meter. So the goal of this algorithm is to identify.
Dr. Mohammed, we will have less than 5 minutes, please.
Less than?
5 minutes, less than 5 minutes, please, just to wrap up your presentation, please.
Yeah, that's fine. I'll try just to skip all of these. So I'll just, here we have, here is our 2 algorithm, but here is our simulation. We just go to our simulation. So this one here. So in this one here, this is our second one, settings. Yeah, so this one here, for this one, after as I said here, we developed 2 algorithms here, this one and the next one, and after that we basically deploy nodes in also different scenarios. We try to basically to be a little bit rational and to imitate or just to be realistic. So in this one, we first deploy 36 and 66 and 125 homogeneous node. Secondly, we deploy 36 and also 66 and 125 homogeneous nodes, assuming processing of power candidate computer is limited. So finally, we also deploy 36 and 66 and 125 nodes heterogeneously in terms of data size for every computer holding the same assumption. So our goal is basically to allocate every master node to a computer. We do not know the number of candidate computers in advance. So the location of the deployed nodes is fixed in our 3 experiments. The size of the data, the size of the system or the network is set to 600 square. So the simulation settings here, we have we specify our communication range, and we have also some information here about the initial power for every device. But if let us move on just to the result. So for the algorithm one, our first experiment here is homogeneous node, and nodes are deployed in the network areas as depicted in figure 1 and figure 2 and figure 3, all of these figures. So our goal, as I said before, in this experiment is to group master node into groups based on the communication range explained in algorithm 1. So number of computers should be as minimum as possible. So we succeed to allocate every single master node to a computer based on the communication range. However, we observe that the load is not well balanced among the computers after the allocation process. So the rationale behind this is that the algorithm after convergence checks if a computer has a threshold of a master node, then the whole group merged with a group that computer CI falls into initially. So the second simulation here, so in order just to be a little bit realistic, so and to because as we know most of the resources are limited, so in real life everything is limited, as I said. So therefore, in our second experiment, we add constraint to the processing power of candidate computers. So we observe that the number of computers increases compared to the previous scenarios, as you can see in these figures. So it is basically due to the process of defining the areas to sectors. So however, the load balance is improved. There is no congestion at all candidate computers because the total of received data at every computer is less than its capacity. The last one here. So we decide just to really relax the constraint in the previous experiment to see the behavior of our algorithm. So we observe that the number of candidate computers increases less than our second scenarios because master node deployed heterogeneously and the convergence of every cluster doesn't happen as fast as second scenario. So in conclusion, around 70% of the planet is covered by water. So it is very difficult to monitor or detect a change in underwater environment by simple sensor without a complete full network. So as a result of having such huge covered area covered by water, so we in need of having real-time technologies that can report responsible organization sectors about any change or phenomena that happens in the underwater environment. So underwater wireless sensor network technology can replace traditional approaches by offering real-time monitoring for underwater environment. So because of that, considerable attention has been drawn to applications regarding underwater wireless sensor network, such as object detection, seismic monitoring, oil pipeline monitoring. So based on that, on the cutting edge researches, so in this field, we continued their work and we made key improvements on the reliability of the system and the end-to-end delay of the network. The last one here, sorry, Dr. Yusuf, the last slide. So in this dissertation, just right now, I will just try to cover what we did in our research. So in this dissertation, we started our journey by developing an efficient architecture in order to increase the reliability of the previous developed system. So after that, we developed a fault detection and recovery algorithm to secure our system from failure when it happens. Next, we developed 3 different topologies, and we studied the performance of our system in each one of them. After that, we developed multiple efficient algorithms to find the best number of computers to be deployed in our system. We succeed to increase the reliability of the system by around 50% comparing to the baseline system, and also we succeed to minimize the end-to-end delay of the network. So here is my publication list, and thank you so much for attending and my presentation.
Thank you so much, Wallah, Dr. Mohammed. This was really interesting topic and very informative presentation, mashallah. Now we will have some questions from the audience. If anyone has any question, please go ahead, open your mic and ask the question. I believe that we have a few faculty members here who are really specialized in networks, like Dr. Majdoub and Dr. Jberi. So we're assuming that some people will have some questions.
السلام عليكم.
السلام ورحمة الله
عليكم
وبركاته.
السلام.
دكتور محمد تفضل.
حياكم الله. First of all, Dr. Mohammed, يعني I would like to say يعني congratulations on your PhD achievement and welcome back to your home. I think we are all proud of you, Dr. Mohammed. I want to say يعني this thing to you, and I will let يعني the other colleagues to if they have any questions or any comments upon your PhD presentations. I wish you all the best, Dr. Mohammed. Inshallah, see you soon, inshallah, in the college.
Thank you so much, Dr. Mohammed. Thank you so much.
السلام عليكم.
وعليكم السلام.
ورحمة الله. تفضل دكتور مجدوب.
الله يسلمك يا دكتور يوسف. السلام عليكم ورحمة الله وبركاته. First of all, thank you for your informative presentation. Secondly, congratulations on finishing your PhD. Very interesting topic and very full of information presentation. Can you please go to slide number 76?
Yes.
Just I didn't get this point. Point number 3, limited processing power for candidate computers. Can you elaborate more, please?
Yes, basically, the amount of the data a computer can process in a unit of time.
So these computers will get this data from the sensors.
No, this computer will get the data from the master node. We have three layers. The first layer, we have the sensor node, the regular sensor node. So after that, we have another layer called master node, or we call it cluster nodes. So these cluster nodes, their job or their task is basically to collect the data from every sensor node based on the range of this master node. So we have another, also we developed some other techniques for these. But the second level is the master node. Their task is only to collect the data from the sensor node and then transmit this data to the computer. So we decide to use a computer in the bottom of the ocean in order basically to, as you know, if we transmit a huge observation or phenomena from the bottom of the ocean to the control station without processing these data before we submit it, it will take a long time. So because of that, we and the researchers before me, they developed a processing machine called computer. It's a third level, and it's tasked to collect the data from the master nodes only, and they process the data using some feature extraction algorithms, and then submit only or transmit only to the gateway the valuable information. Make sense?
Yes. Now it is crystal clear. Jazakallah khair, doctor, and congratulations again.
Allah يحييك. حياك الله. Thank you so much.
جزاك الله خير دكتور مجدوب. Any other question, please? Dr. Al-Jubairi, I think Internet of Things, wireless networks is also your specialized area. So if you have any question for Dr. Alsulami.
Thank you very much, Dr. Yusuf. I'm not sure, do you hear my voice or it's not clear?
Yes, it's clear, Dr. Mohammed.
Sorry, I can't hear. Is it clear?
Yes,
Yes,
clear.
it's clear, Dr. Mohammed.
Yeah. Thank you. First of all, I would like to thank Dr. Mohammed Alsulami for his brilliant presentation. It's very solid and very interesting. I'm just wondering what type of wireless did you use, Dr. Mohammed? Is it cellular or Wi-Fi, or what type of wireless communication?
Assume we will use only Wi-Fi. This is what we assume. So this technology, Dr. Mohammed, it's a new technology. So what right now the countries or people or government they use? They only use something called AUVs. So these called basically stands for autonomous underwater vehicle. So the task of these AUVs right these days is basically to visit every single sensor node and collect the data from every single sensor node. So this process, it will take a long time. So because of that, this system right now, this is such system, it doesn't meet the real-time constraints. So because of, most of the time, if you are, for example, looking for a hard real-time systems, for example, if you are deploying these sensor nodes for example, in any, for example, in our East Coast side of our country, for example, yeah. So maybe we have some enemy from around our country, for example, Iran, right, these days. So we have as a solution for in order to not deploy soldiers and thousands of soldiers, you can basically right now deploy this sensor node and develop a network for that. And from there, you can get anything coming through your border in real time.
That's perfect.
Makes sense?
Yeah, thank you. Perfect. Thank you very much.
Thank you so much, Dr. Haif and Dr. Mohammed. Please mute your mic, Dr. Mohammed Haif, so we can have another questions from others.
There's another defense, Dr. Yusuf.
Sorry, Dr. Mohammed Haif. I was saying Dr. Mohammed Haif. Yes, of course, it's not another defense, Dr. Mohammed Alsulami. But I always think that many questions from others means that it's a very interesting topic, and many people are really interested in your presentation, mashallah.
الله يجزاك خير. If you allow me, Dr. Yusuf.
Yes, please, Dr. Hani, تفضل.
السلام عليكم. أسعد الله مساكم جميعا بخير. Thank you so much, Dr. Mohammed, for this, mashallah, beautiful and great and informative presentation. Thank you so much. May Allah reward you with all the best that you're looking for. I just want to say congratulations for your achievement, and inshallah see you soon, inshallah, in the college. I do not have any question right now, but inshallah when we see you, inshallah we'll get more inshallah comments, or we will discuss this inshallah soon, inshallah, together. Thank you so much.
Thank you so much, Dr. Hani.
Thank you.
Okay, any other questions from the audience, please? Any other questions?
Can I add something here, Dr. Yusuf?
Yes, please. Yes, please.
Yeah, so I got a question last week from one of my friends. So they said how to deploy a computer in the bottom of the ocean or on the bottom of the sea. So it was a good question. So we got the idea from Google. Google company, they started not long time ago. They start deploying their whole data centers, the whole data center in the bottom of the ocean, in order just to reduce the cost or the money that they paid for the power for this system. So it is something is basically doable, and something that we can, I think, we focus, or for example, for private sectors, they focus on it, we can do something, or the people they are working on this and such research, they can do something.
Very nice, Wallahi, Dr. Mohammed, mashallah. Okay, any other questions, please? Okay, I think that's all. Thank you again, Dr. Mohammed. This was again a very nice presentation, and really enjoyed every bit of the talk that you gave today. And welcome back. Congratulations again for completing your PhD. We are very happy for you and so proud, as the Dean said. And wallahi, waiting really to work together again. I'm very sure that you are going to be a very valuable addition to the college and also to the university, inshallah. Thank you so much again, Dr. Mohammed. And that's all for today. Thank you so much.
Okay, Dr. Yusuf, thank you so much.
Thank you, Dr.